Welcome back to Physics 191. I'm Gerard Blanchard, and we're going to resume our discussion of forces that you'll encounter. Once again, this is not an exhaustive list of forces. There are many forces that we'll introduce as classes go on, and if you take Physics 192, you'll encounter even more. We left off discussing friction. The next force in our list is tension. Tension is the force exerted by a rope or a string on an object. We'll write tension with a capital T with a vector on it. The magnitude of the tension is whatever it happens to be from the situation. So all we can say is that it'll be equal to its magnitude, T, and when its magnitude, we'll italicize. That differentiates magnitude from the vector. So a capital italic T is the magnitude of tension. And once again, just like normal force, we have to determine its magnitude from the situation that we're in. Actually, we'll determine it from Newton's first law, or maybe second law. What we do know about tension is that the direction of tension will be in the direction of the rope. If the rope is pulling horizontally, then the tension force will be horizontal. If the rope is pulling vertically, then the tension force will be vertical. If it's pulling at an angle, then the tension force will be in the direction of whatever the angle is. And you'll see some examples of that soon. And finally, the last force that I have in my list is something I'll call the applied force. That's the force of everything else acting on our object. So for example, last time I was pulling on some boxes. Well, my force would be the applied force. Now, with that list of forces, we are ready for Newton's first law. Once again, this is a mark of genius for Isaac Newton that he formulated this law. It replaced ideas that had persisted for a couple thousand years, about 2,000 years. People thought incorrectly about objects and forces, and Newton had the insight to write down his first and second and third laws, and that really helped us to understand how objects move. I'll spare you the Latin with which Newton wrote his first law, but a direct translation of Newton's first law from Latin would be, every body perseveres in its state of being at rest or of moving uniformly straight ahead, except insofar as it is compelled to change its state by unbalanced forces. I'm going to read that again and let's think about it. Every body perseveres in its state of being at rest or of moving uniformly straight ahead. Now that would be an object at rest remains at rest, or an object in motion remains in motion at constant speed in a straight line, except insofar as it is compelled to change its state by unbalanced forces. So an object at rest remains at rest, or an object in motion remains in motion, unless there are unbalanced forces on the object. So rewriting that and paraphrasing, I would say in equilibrium, which means that an object is at rest and remaining at rest, or moving in a straight line at constant speed. So in equilibrium, all of the forces on that object are balanced. Or simply, we can write that as an equation, and that'll be our first physical principle expressed as an equation. In equilibrium, the total force vector on an object is equal to 0. So in equilibrium, the total force vector on an object is equal to 0. Now, the first thing I'll remind you is to be careful. equilibrium is not just at rest and remaining at rest. Most people are comfortable with the idea of being at rest and remaining at rest being equilibrium. But also, if an object is moving at constant speed in a straight line, it's also in equilibrium. So at rest and remaining at rest is equilibrium. Moving at constant speed in a straight line is also equilibrium. We give those two names to help you remember both of them. At rest and remaining at rest we would call static equilibrium. Moving at constant speed in a straight line we call dynamic equilibrium. So remember, dynamic equilibrium is also equilibrium. And in equilibrium, the total force vector on the object is equal to 0. So that gives us our first situation, our first type of situation, which I will call equilibrium situation. And we will have several of these types of situations as we go on through the course. This is just the first. So the first type of situation is equilibrium. How do you identify an equilibrium situation? Well, you have either static or dynamic equilibrium, which means that the object under consideration is at rest and it remains at rest, or it's moving at constant speed in a straight line. And so when you have an equilibrium situation, you can write your equilibrium equation. And your equilibrium equation is total force vector is equal to 0. That is actually, remember that every vector equation is two equations, that's actually two equations. Total force in the x direction is 0, and separately, total force in the y direction is equal to 0. Let's put that to work. I'm going to give you a situation which is an equilibrium situation. And what it is we have a 2.0 kilogram ball tied to a string fixed to the ceiling, and it's pulled to one side by a force. Just before the ball is released, how large is the force that is holding the ball in position, and what is the tension in the string? You can see a diagram there. But let's redraw the diagram. Remember that our first step in solving any situation is to draw a diagram. So I will redraw that diagram for you. And the first thing to ask ourselves is, what is the central object that's under consideration here? What is the object that all of the forces are being exerted on? And in this case, it's the ball. So we have, I'm going to draw the ball in the center. We have an applied force that is to the right, and we'll call that our x direction, and our y direction. We know that the mass of the ball is 2 kilograms, so that lets us know that there is also weight to be considered. So I have to draw in the weight as well. Well, we know which direction weight is exerted, and that is straight down. And we know that weight is equal to the mass of the ball times g, straight down. And we can go ahead and calculate the weight. The weight would be 2 kilograms times 9.80 newtons per kilogram. We're assuming that we're working at the surface of the Earth, so near the surface of the Earth, the gravitational field strength is always 9.80 newtons per kilogram. Once again, I haven't drawn in my units into this equation just for clarity's sake. And so we can write that the weight is equal to 19.6, and we know that the units are newtons since we know that we're working in basic metric units. Now there is one more force to consider here, and that is the string, the tension of the string. And I will draw the string in. And we were told that the string makes an angle of 30 degrees with the ceiling. Since the ceiling is parallel to our x-axis, we know that this angle here will also be 30 degrees. And we also know that the tension will be pulling in the direction of the string. So I will just draw in, let's draw in tension like this. So that is our first step. And have we gotten all the information from the problem statement? Yes, we have. We have the ball, we have the string pulling at an angle of 30 degrees. We have the mass of the ball. So we've drawn our diagram, we've drawn in all the forces acting on the ball, and we've gotten everything that's known from the statement. What are our unknowns? Well, our first unknown is the applied force. What is the applied force? What is the tension? That's our other unknown. So we have two unknowns here that we're looking for. What can we do? Well, from algebra we know that if we have two unknowns, we have to have two equations. What are our two equations? Well, that's where we bring physics into the situation. That's where we bring Newton's first law. The ball is at rest and it remains at rest. So the ball is in static equilibrium. So in that case, we know that the total force vector on the ball is 0. So we have static equilibrium and we know from Newton's first law the total force vector is equal to 0. And since that's a vector equation, it's actually two equations. Force total in the x direction is 0, and force total in the y direction is 0. So a vector equation is two equations. And since we have two unknowns and two equations, we'll be able to solve. Well, let's look at our forces in the x direction. What forces do we have in the positive x direction? Well, our applied force is completely in the positive x direction. It's completely in the x, so all of the applied force is in the x direction. So I can write for force total x, I can write force applied. Do I have anything else pulling the ball in the positive x direction? Well, no. Weight is pulling down. That's in the negative y direction, so that's going to go into our y equation and not in our x equation at all. Tension is pulling in the negative x direction. So we don't have anything else pulling in the positive x direction, but we're going to have to subtract off the tension. Not the whole tension, but only the amount of tension that's pulling in the negative x direction. Well, what do? We have to break our tension down into a right triangle. We have to make a right triangle. We have to take our tension, that is up and to the left and turn it into a left part and an up part. The And we can call it, since we have a right triangle and our 30-degree angle is here, this would be T adjacent, the amount of tension adjacent to the angle. T opposite, the component of tension opposite the angle. And what we will have to subtract off is the adjacent component in our X equation. So our X equation is the applied force minus tension, the adjacent component of the tension, is equal to 0. Or if I add tension adjacent to both sides, I would see that the applied force is equal to the adjacent component of the tension. And all I did there is I added T adjacent to both sides. And so the applied force, well, tension adjacent is equal to the hypotenuse times the cosine of the angle. So that would be tension times cosine of 30 degrees. Well, we don't know tension, so we can't do anything else with our X equation at this point. What do? Let's try our Y equation. Let's see what our Y equation will give us. Because right now in our X equation we have force applied, which is an unknown, tension, which is an unknown. That's two unknowns in one equation. Let's try our other equation. Let's look at our Y equation. What do we have pulling in the positive Y direction? What is pulling the ball upwards? Well, that would be T opposite. T opposite. Is anything else pulling the ball up? No. Weight, however, is pulling down. So it would be T opposite minus the weight. And we know what weight is. Weight is 19.6 newtons. So T opposite minus 19.6 newtons equals 0. Or, by adding 19.6 newton to both sides, we see that T opposite is equal to 19.6 newtons. So we know that this component of the tension must be 19.6 newtons. We're getting somewhere. Now, we also know that T opposite is equal to the hypotenuse, which is T, times the sine of theta. So T sine of 30 degrees is equal to 19.6, or the tension is equal to 19.6 divided by sine of 30 degrees. 19.6 divided by sine of 30. And that is 39.2 newtons. So the tension is 39.2. Now, why is tension bigger than weight? Well, the tension is not completely pulling against weight. Only part of the tension is pulling against the weight. So if this is what is counteracting the weight, then the tension, the total tension in the rope must be even bigger. So the tension in the rope is 39.2 newtons. Now we can calculate the applied force. The applied force is tension, which is 39.2, times the cosine of 30 degrees, or the applied force is equal to 39.2 times cosine of 30 degrees. And that would be 33.9 newtons. So we have answered the question that was put to us. What is the tension in the rope in this situation? 39.2 newtons. What is the applied force? 33.9 newtons. And how did we do that? We did that by drawing a diagram, drawing in the forces, identifying the situation as an equilibrium, a static equilibrium situation, and writing down our starting equation. Total force vector is 0, and the total force vector equals 0 is actually two equations. Total force in the x direction is 0, total force in the y direction is 0. Had two equations and two unknowns, so from that point we just worked through our algebra and we got to the answer. Let's try another example. In this case, we have two boxes with different masses that are tied together on a frictionless ramp surface. And the question is, what is the tension in each of the cards? Well, let's just start with one box. Let's just consider the 2 kilogram box that you see there. There's a rope attached to the 2 kilogram box. What is the tension in that rope alone? And we also see in the diagram that the slope of the ramp is 25 degrees. So before I let you work on this, I'm going to get you started. The first thing we always do, is we draw a diagram. We'll draw our ramp. .25 degrees. We'll draw in the box. And we'll draw in the rope pulling on the box. Okay. Next, we have to consider our forces. What are our forces on the box? Well, obviously, we have tension in the direction of the rope. We also have the normal force from the ramp. And we know that the normal force is going to be perpendicular to the ramp. So the normal force is pushing the box upward in the direction perpendicular to the ramp. And finally, what other force do we have on the box? We have the box's weight. What is the direction of the weight? It's straight down. So we have weight, and we know that weight is equal to mass times our gravitational field strength. We know the mass of the box. We're given that the mass of the box is 2 kilograms. So we know that the weight of the box is 2 times our gravitational field strength of 9.80, or the weight is 19.6 newtons. Okay. The box is at rest, or remains at rest. So we know that we once again have a static equilibrium. Have a static equilibrium situation. We know that when we have a static equilibrium situation, we have the total force vector is equal to 0. And we know that the total force vector equal to 0 is two equations. Force total x is equal to 0, and force total y is equal to 0. So we have two equations. We can solve for two unknowns. What are our unknowns? Well, tension. We're being asked for tension. That's one of our unknowns. And we also don't know what the normal force is. So that's our other unknown. What I haven't done yet is I haven't drawn in my x and y axes. You might think to draw them horizontally and vertically like we usually do, but I'm going to show you a trick here that'll help you. what I will do is I'm going to turn the page sideways. I haven't really changed anything. The forces are still acting on the box. What I've done now, though, is now I've made tension horizontal, I've made normal force horizontal, and I've rotated weight so that the weight is down and to the left. And now I'm going to draw my x and y axes like this. X along the ramp and y in that direction. Now the reason I've done that is that now two of my forces are completely in the direction of my axes. Tension is completely in the x direction, normal force is completely in the y direction, so I don't have to break them down into triangles. Now I only have one angle to break down, one vector to break down into a triangle, and that would be my weight. So now I want to break my weight down into horizontal and vertical components. Well, weight, now that we've rotated the page, is down and to the left. So I'm going to break that up into something that is to the left and down. If I had drawn my x and y axes otherwise, then I would have had to break down both tension and the normal force, but now I only have to break down the weight. Well, I need an angle. You can see here that we have a right triangle right here. This is my 90-degree angle. This angle over here is 25 degrees. This angle up here would be 90 minus 25. So we're going to make that our angle for our triangle for weight, and that would be 65 degrees, or 90 minus 25. So that is 65 degrees. And we have this side would be weight adjacent, and this side would be weight opposite. Now that I've done all of that, I can rotate back. And we can work. I would like you to try this. Try to work out force total x is equal to 0, force total y is equal to 0, and see if you can find tension and the normal force. Okay, I am going to rewrite force total x equals 0 and force total y is equal to 0 to give myself a little bit more space to work. Force total x is equal to 0. Force total y is equal to 0. Now, what forces do we have pulling in the x direction? Well, remember that x is parallel to the ramp now, and in the positive x direction we have tension. So we have tension pulling up the ramp, and weight, or at least the adjacent component of weight, is pulling the box down the ramp. So that would be tension minus weight adjacent is equal to 0. Or, adding weight adjacent to both sides, we have tension is equal to weight adjacent, or tension is equal to weight adjacent. Weight adjacent is this side adjacent to our 65-degree angle, so that would be equal to our hypotenuse, which is down here, which is the total weight. Tension is equal to 19.6, which is our total weight, times the cosine of 65 degrees, or the tension is equal to The tension is equal to 8.2, we'll call it 8.3 newtons. And so that's how we solve for the tension. You'll do something very similar for the normal force. Well, actually we don't even need to find the normal force because what we were asked to find was the tension. So we've actually answered the question already. We don't need our y equation. You'll find that that happens sometimes. But just for practice, let's find out what the normal force is. Try to find out what the normal force is. Well, the normal force we'll find out from our y equation because the normal force is pulling completely in the positive y direction. So we have normal force pulling in the positive y direction, and pulling against the normal force is weight opposite. So normal force minus weight opposite is equal to 0, or normal force is equal to weight opposite, or the normal force, this is weight opposite, it's equal to the hypotenuse of 19.6 newtons times the sine of 65 degrees. So the normal force that the ramp exerts on the box is 19.6 times sine of 65 would be 17.8 newtons. So from our two equations, we were able to figure out two unknowns, tension and normal force. We weren't actually asked for normal force, but we did that for practice. And if you wanted to, you could go on and repeat this process to find the forces on the other box. But let's try another example. In this example, we have a computer weighing 87 newtons. Note that it gave us the weight this time. It didn't give us the mass, so we're already given the weight. A computer weighing 87 newtons rests on the horizontal surface of your desk. The coefficient of friction between the computer and the desk is 0.6. Well, I mean the coefficient of static friction between the computer and the desk is 0.6. And the question is, what is the largest angle that you can tilt your desk before the computer will start to slide? Well, let's draw out the diagram first so we can see what we're talking about here. I'll draw a tilted desk. We have the computer. We're tilting it to some angle theta, which we don't know. We have, what are our forces acting on the box? Well, we know that we have the weight of the computer, and we know that weight goes straight down. And we were told that weight is equal to 87 newtons. We know that the normal force of the desk will act perpendicular to the desk. That's our normal force, and we don't know what that is. And we also know that we'll have friction. We'll have static friction in this case, and we know that static friction acts parallel to the desktop. So it will act in this direction, in this case, because we know that weight will act to pull the computer down the ramp, so we know that friction will act against it, and that will be static friction. And we know that static friction is less than or equal to the coefficient of friction, coefficient of static friction, times the normal force, which means that we know that the static friction force is less than or equal to 0.6 times the normal force. We have to draw our x and y axes, and once again, since we have something parallel to the desktop, something perpendicular to the desktop, I would advise you to rotate your diagram like this, rotate all of the forces, that's allowed, and make your x-axis along the ramp, your y-axis perpendicular to the ramp, and then the static friction force becomes completely in the x direction, the normal force becomes completely in the y direction, and the weight now has rotated so that it is down and to the left. So we have to break it into a triangle that is down and to the left. So this becomes our right triangle right here. The hypotenuse is the weight. Our angle, actually, if we use this angle right here, I'm going to call that theta 2. We'll call that theta 2 since we don't know what it is, but we know that theta 2 is equal to 90 degrees minus theta. This angle right here is 90 degrees minus this because we actually have a right triangle right here. Okay, we can rotate our page back. We have to ask ourselves, what type of situation is this? It's a static equilibrium situation. Static equilibrium, and we know when we have static equilibrium we can write, and I'm just going to skip right ahead to force total x is equal to 0 and force total y is equal to 0. We can use that to actually answer the question. You might not see how at first, but I would like you to work and see how far you can get towards answering the question of what is the greatest that theta can be before the computer slides on the desk. Okay, well, once again I'm going to rewrite force total x is equal to 0, force total y is equal to 0. Those are our starting equations, as they always are when we have static equilibrium. What forces do we have in the positive x direction? We have the static friction force pulling in the positive x direction. And for the moment, I'm just going to write that as F static. What do we have pulling in the negative x direction? Well, we have weight adjacent. So static friction force minus weight adjacent is equal to 0, or we know that the static friction force must be equal to weight adjacent, or we know that the static friction force is equal to the weight, the hypotenuse, 87, times the cosine of theta 2. Well, what can we do with that? We know that the static friction force must be less than or equal to 0.6 times the normal force. So we know that 87 times the cosine of theta 2 must be less than or equal to 0.6 times the normal force. So once again, we still have two unknowns here. Let me write my force static friction. We still have two unknowns here. We have theta 2 and we have the normal force. And that's not newtons now. Be careful. That's not newtons. That is 0.6 times the normal force. Well, where are we going to get our normal force from? We'll get that from our y equation. Our y equation would be normal force pulling up in the positive y direction minus weight opposite is equal to 0, or normal force is equal to weight opposite, or the normal force is equal to 87 newtons times the sine of theta 2. What can we do with that? Well, we can take normal force and put it into this, well, now it's not an equation, it's an inequality. And so we have 87 cosine of theta 2 must be less than or equal to 87 sine of theta 2. Wow, what can we do with that? Well, I'm going to divide both sides by 87 cosine of theta 2. And 87 cosine of theta 2 divided by 87 cosine of theta 2 is, oops, actually I'm sorry, I lost my 0.6. This was 0.6 times the normal force, so I lost my factor of 0.6 right here. 87 cosine of theta 2 times 87 cosine of theta 2 is 1, and that has to be less than or equal to 87 divided by 87 is 1. Sine of theta divided by cosine of theta 2, sine of theta 2 divided by cosine of theta 2 is tangent of theta 2. And then we still have our coefficient of friction times 0.6. Well, I'm going to divide both sides by that 0.6. And I have 1 divided by 0.6. And what is 1 divided by 0.6? Is we'll call it 1.67. Has to be less than or equal to the tangent of theta 2. Well, I can take the inverse tangent of both sides. The inverse tangent of 1.67 has to be less than or equal to theta 2. And what is the inverse tangent of 1.67? That would be 59.1. So 59.1 degrees has to be less than or equal to theta 2, or I can write that as theta 2 has to be greater than or equal to 59.1 degrees. So the maximum that theta 2 can be is 59.1 degrees. And since theta 2 is related to the angle of the desk by theta 2 is 90 degrees minus the angle of the desk has to be greater than or equal to 59.1 degrees. What I will do is I will subtract 59.1 from both sides and add theta to both sides. And so I'll have 90 degrees minus 59.1 has to be greater than or equal to theta, or or 30.9 degrees has to be greater than or equal to the angle of the desk. Or in other words, the angle of the desk can be no more than 30.9 degrees or the computer will slide. That's it for this session. I'll see you next time, and remember, think physics.